On this channel, we have covered most of the recent papers that discuss and explain how fast the universe is expanding and why it is expanding faster and faster over time. These are some of the most fundamental topics in cosmology, the study of the origin and evolution of the universe. As mentioned previously, there is a problem: different methods of measuring the expansion rate give different results. This is called the Hubble tension, and it is one of the biggest mysteries in modern physics. However, a new paper published in the journal Monthly Notices of the Royal Astronomical Society suggests a surprising and intriguing answer: maybe we live in a giant void, a region of space that is less dense than the average. In this video, we will explore this research and see how it could explain the Hubble tension and the observed motion of galaxies in the nearby universe. We will also discuss the challenges and implications of this hypothesis and what it means for our understanding of the universe. The expansion rate of the universe is also known as the Hubble constant, named after the astronomer Edwin Hubble, who discovered that the universe is expanding in 1929. It tells us how fast the space between galaxies is stretching, and it depends on the distance and the speed of the galaxies. The farther away a galaxy is, the faster it is moving away from us due to the expansion of space. There are several ways to measure the distance and speed of a galaxy, but the two most commonly used are based on the cosmic microwave background, CMB, and the Type 1a supernova. The CMB is the oldest radiation in the universe, emitted about 380,000 years after the Big Bang, when the universe became transparent to light. It is like a snapshot of the early universe and contains tiny fluctuations in temperature and density that reveal the properties of the universe at that time. By analyzing the CMB data from the Planck satellite, which mapped the CMB with unprecedented precision, we can infer the Hubble constant and other cosmological parameters, such as the density and composition of the universe. Type 1a supernovae are exploding stars that have a very consistent brightness, which makes them ideal for measuring distances in the universe. By comparing the apparent brightness of a supernova with its intrinsic brightness, we can estimate how far away it is. By measuring the redshift of its light, we can estimate how fast it is moving away from us. By combining the distance and the speed of many supernovae, we can calculate the Hubble constant. The Pantheon sample is the largest and most recent collection of Type 1a supernova data, containing over 1,000 supernovae from different surveys. Both the CMB and the supernova methods are very reliable and accurate, but they give different values for the Hubble constant. The CMB method gives a value of about 67 km per second per megaparsec, while the supernova method gives a value of about 74 km per second per megaparsec. This difference is not due to random errors or systematic uncertainties, but it is statistically significant and persistent. This is the Hubble tension, and it implies that there is something wrong with our standard model of cosmology, or that there is some new physics that we are missing. But there is another piece of the puzzle that we need to consider: the motion of galaxies. Not only are galaxies moving away from us due to the expansion of space, but they also have their own peculiar velocities due to the gravitational attraction of nearby matter. These peculiar velocities can affect the measurement of the Hubble constant, especially for the supernova method, which assumes that the galaxies are only moving due to the expansion of space. If we do not correct for the peculiar velocities, we may overestimate or underestimate the Hubble constant, depending on the direction and magnitude of the motion. So how can we measure the peculiar velocities of galaxies? One way is to use the Cosmic Flows 3 catalog, which is the largest and most comprehensive catalog of galaxy distances and velocities, containing over 17,000 galaxies within 300 megaparsecs from us. By comparing the observed velocities of galaxies with the expected velocities from the expansion of space, we can estimate the peculiar velocities of galaxies and correct for them in the supernova data. When the authors of the paper did this, they found something surprising and intriguing. There is a significant and coherent motion of galaxies within 250 megaparsecs from us, which is the largest coherent motion ever detected in the local universe. This motion is called the bulk flow, and it means that the galaxies in this region are moving in the same direction and with the same speed relative to the average motion of the universe. The bulk flow is not random or isotropic, but it is aligned with a specific direction in the sky, which points towards the constellation of Centaurus. The authors used a Bayesian model to account for the bulk flow in the supernova data, and they found that this reduced the Hubble tension significantly. By correcting for the bulk flow, the Hubble constant from the supernova method decreased from 74 to 69 km per second per megaparsec, which is much closer to the value from the CMB method. This means that the bulk flow is a major source of the Hubble tension and that by accounting for it, we can reconcile the different methods of measuring the expansion rate of the universe. But what causes the bulk flow? Why are the galaxies in the nearby universe moving in the same direction and at the same speed? The authors of the paper proposed a simple and elegant explanation: maybe we live in a giant void, a region of space that is less dense than the average. This void is called the local void, and it is one of the largest structures in the nearby universe, spanning about 150 megaparsecs in diameter. It is located in the opposite direction of the bulk flow, which means that the galaxies in the bulk flow are moving away from the local void due to the gravitational pull of the surrounding denser regions. However, according to the paper, the local void is not a perfect vacuum, but it is a region where the density of matter is about 20% lower than the average density of the universe. This may not seem like a big difference, but it has a significant effect on the expansion rate and the gravitational potential of the local universe. The expansion rate is faster inside the void because there is less matter to slow it down. The gravitational potential is lower inside the void because there is less mass to bend the spacetime. These effects can explain the bulk flow as well as the Hubble tension. The authors of the paper used a simple model to estimate the properties and location of the local void and how it affects the Hubble constant and the bulk flow. Surprisingly, they found that the local void is centered at a distance of about 70 megaparsecs from us and that it has a density contrast of about 0.2, which means that it is 20% less dense than the average. They also found that the local void can explain the observed magnitude and direction of the bulk flow and that it can reduce the Hubble tension by about 70%. This means that the local void is a plausible and consistent solution to the Hubble tension and that it reveals the existence and influence of a large-scale structure in the nearby universe. Thank you for watching this video. I hope you enjoyed it and learned something new. If you did, please like, share, and subscribe to this channel for more videos on astronomy and cosmology. If you have any questions or comments, please leave them below, and I will try to answer them. See you next time. Enjoy.